So, in the last section, we talked about relative age dating, where scientists use things to get an approximate age, like these rocks are older than that rock because they cut through it, or whatever. So, it's kind of a comparative age way of telling the age of something. But sometimes scientists want to be a lot more precise in knowing exactly how old something is, and so they use different methods, and one of them is called radioactive decay. So, in this section, we're going to talk about absolute dating methods, and absolute dating methods give scientists the um, just a lot more precise age of the things that they are studying. So, the first one that we're going to look at, which is radioactive decay. Over time, things will decay. Elements and isotopes will actually decay from one isotope to the next isotope over time. And as time passes, it will decay more and more. So, radioactive decay is very reliable because it happens or it moves in a very fixed way, like a clock. It's very dependable. It doesn't have times of like speeding up or slowing down. It's just very regular, so can give very accurate measurements. So in this example, I'll show you uranium 238 actually has an extremely long half-life. We'll talk about that right here. Uranium 238, which we started with here, it has a half-life of 4.5 billion years. And because it has such a long half-life, it basically is used to measure things that are very, very old because of how long it takes to decay. So going back up here, as the amount of so like uranium 238, let me get back up to this picture. Uranium 238 first decays to thorium 234. So as time passes, the amount of uranium will go down, and the amount of thorium in the rock sample or fossil will actually increase. So this is another way of showing that same thing. If we start off with a parent isotope of, say, uranium of 238, then in the beginning it's going to be all uranium. Say these orange colored balls are uranium. After one half-life, where half of it is left, excuse me, you're going to have about 8 uranium left and about 8 thorium left. And after another half-life, you're going to cut the number 8 in half. So now we're at 4 uranium left, which means we're at 12 thoriums that are left. So it regularly splits in half, and for uranium, that's every 4.5 billion years. So if the uranium is full uranium, then we know we are at time zero, or the sample is pretty brand new, is fairly brand new. But if we had about half the amount of thorium or uranium compared to thorium, then we would know, if it was about half and it had gone through one half-life, we would know that the sample was about 4.5 billion years. And if it was about 25% uranium and 75% thorium, we would know that it had gone through another half-life. So 4.5 billion years plus 4.5 billion years, which would be 9 billion years. Old would be the sample. So I kind of want to show you what that would look like. And I gave you the example here of thorium, which has a half-life of 14 billion years. Okay, so if we started here at thorium and we had 14 billion years, is the lifespan of the isotope, um, or the length of time for a half-life. So maybe I should put that. Length of time for one half-life of the isotope. Okay, so if the amount of the isotope at the beginning, if there's 100% thorium, the amount of time that has passed, if it's 100%, is 0. And the amount of the, and then if we're going to have a half-life, what's the amount of the isotope in percent that's left at the end of the half-life? Well, if we cut this 100% in half, there's going to be 50% after one half-life. So how long has it been then? So if it's 14 billion years for one half-life, it's been 14 billion years at this point. So now we have the amount left is 50%. So now the amount of time that has passed, we're going to bring this down, is 14 billion years. And that's why we only have 50% left. If we put this through another half-life, we're going to take this 50% and cut it in half. And half of 50% is 25%. And then we're going to take this 14 billion years and we're going to add another 14 billion years to it, because that's how much time has now passed. So that's 28 billion years. So now we're going to bring these down. Now it's been 25% and 28 billion years. And now we're going to cut this 25% in half again, which what's half of 25? The answer is 12.5%. And now we're going to add 14 billion years onto this 28 billion years, which is 28 plus 14. That's going to be 42 billion years. So if you had a sample that had about 12.5% of the thorium left, you would know that it was about 42 billion years old. By filling out this table and doing something like this, for each half-life, you're going to add the 14 billion years. So that's how you solve a problem in how to do that. Moving back, a lot of these are in billions of years, which means they're for very, very, very old samples. But one of them kind of stands out, carbon-14. Excuse me. Carbon-14 decays. It only takes 5,730 years for half of it to decay to nitrogen-14. Well, 5,000 years sounds like a long time, but actually compared to rock age and the dinosaurs and everything else, it's not that long. So things that are very old scientists tend to use these. Things that are very young, like things that are maybe 15 to 20,000 years old, scientists would use carbon to date it. And how would scientists know that? Well, they would probably use the relative age, like a good guess of how old it is, to find out, should we pursue it further and see if if it's younger or older, they can pick one or the other of these. Scientists also use tree rings to tell how old things are. Scientists can go in and take a core of a tree and pull it out. It generally, the way that they do it doesn't really harm the tree too much. The tree can generally heal over. But each year trees form 2 tree rings, one more in the wet season where it grows kind of wider, and one that's narrow when it's the dry part of the year. And scientists can also tell how, if there was drought or lots of water based on how much the tree was able to grow. Um, so that's helpful. And that's called dendrochronology, is the dating of trees using that. Scientists can also use ice cores just like that. And the cores that they pull out of ice, it'll tend to have more bubbles in it, and larger ice crystals in the summer. In the winter, it tends to have um, less of that, and ice cores will be like the rings with the wet and the dry. Excuse me. And the last way that scientists do some absolute dating is with varves. Varves basically are deposits of summer and winter, like sediment and dead and decaying plant material. And in the summer, you tend to get much darker soil, and that dark soil, in generally with soil, the darker it is, the closer to black it is, it tends to be a lot healthier, very rich in nutrients and particles. And lighter soil tends to not have as much of that. So scientists can also tell, like, some environmental health things. And you tend to get a more deposits of dead and decaying matter in the summer, just because more things were alive during that time period. So that is it for this section on absolute dating.